mentioned, what I'm going to talk to you today about is building the Milky Way. I think I'm talking to an audience with a very educated background, so bear with me. I tell you a lot of stuff you already know, but hopefully I'll also introduce you to some stuff you're not aware of as well. So when we're talking about our Milky Way galaxy, right, we're one star of billions of stars. We're about 100,000 light years across if you're measuring it in light years. So how did it come to be what it is today? It's had a very complex star formation history, but generally it keeps forming stars throughout its lifetime. When you look at its fuel to form stars, it doesn't have that fuel. So it continually has to be bringing in fuel to form new stars. So that's how you have to build a galaxy, is by bringing in new fuel so that it can continue to grow. It doesn't start with that fuel. So that's kind of the overall theme in terms of the motivation of why we need to understand what I'm going to talk to you about today in terms of how we build it up. I don't think you need the music for this. Let me try to mute it. Okay, it's not responding. It must be hardwired to the it's fine. So this was just starting within our solar system and zooming out. This is a museum. I'm guessing many of you have seen this. This is from the Natural History Museum. They did a nice movie using actual data. And so these are showing you constellations of Zodiac. This is the extent our radio signals have reached from Earth. And then it goes out to give you a perspective of us within the galaxy. And so we're limited, when we study our galaxy, we're limited in a couple ways. We are not limited, and we get a lot more detail than we can see in other galaxies because we're right within it, and so we can map the structures that just aren't visible anywhere else. But at the same time, because we're within it, we have a somewhat obscured view and a unique view in terms of looking at things. So just to explain what we're looking at here, then what it did is it zoomed out from the Milky Way disk, and then you saw the galaxies around it, and then this is the Sloan Digital Sky Survey data showing you each point representing a galaxy, showing you the large-scale structure throughout the universe. And when we talk about building the Milky Way, we're talking about insight into growing galaxies throughout the universe, how this process plays out. So talking about the view, right, we're within the Milky Way galaxy, and so when we're within it, you look in this direction and you see lots of material. You look up, you get a clearer view. This is just one image from, I'm not sure the source on that one, showing you the band of the Milky Way. This is an actual map of the Milky Way from data from the Spitzer Space Telescope and infrared telescope. And so with that, we were actually able to map in more detail the structure of our galactic bar, the structure of our spiral arms, etc., and put that together with radio data and come up with what we think is one of the most accurate representations of our galaxy, which is actually quite difficult, again, because we live within it. So one way we can gain insight into the Milky Way and its growth is by looking at different wavelengths of light. So I mentioned for this map we use infrared data so that we can see through more of the dust. Another place we can look is look at the gas distribution, and with the gas we usually look in the radio or sometimes the millimeter. Right, so in terms of this picture, we're just focusing on the optical wavelengths. We have a very limited view. What we want to do is largely move to longer wavelengths of light because that will make it through much of the dust that is obscuring our view there. Many of you know what you're seeing here is very local to the sun, right? We're seeing only a tiny area within our galaxy when we see this view of the Milky Way. So to see the depth and see all the way to the other side of the galaxy, look up above and see details in terms of what's going on above us, we want to go to longer wavelengths of light. This is just showing you the different ranges of wavelengths of light when you're looking at the moon. So this is going in the infrared, so kind of a heat map of the moon. This is going towards the radio microwave, getting an idea of the temperature distribution across the moon at this time, indicating the sun was over here in this image. This is showing you on the surface, this is the Tycho crater, so getting deeper in where it's a little bit hotter. And then this is a gamma ray image of the moon, showing you the interaction of cosmic rays with the surface, particles on the surface of the moon. So this is just a quick representation giving you a hint of how you use the different wavelengths. You learn something quite unique about the object. So with our galaxy, what we'll do is we'll switch to radio wavelengths. So by radio wavelengths, I'm talking about, I guess it shows up okay. I'll show you a movie of this later as well. By radio wavelengths, I'm talking about going to a wavelength of 21 centimeters. So in the optical, you're talking about a width of approximately human hair. So we're now going to quite a measurable wavelength of light. And with that, we're mapping the cold gas distribution, or the neutral hydrogen, atomic hydrogen, that is the main fuel for all stars, right? The way stars undergo nuclear fusion is through, during their main sequence lifetime, is through the fusion of hydrogen to helium, and that's their most efficient phase of their life when they're undergoing that mode of nuclear fusion. So this is the stuff that fuels all stars, right? And so you start with this, you go from this down to molecular to forming stars, and then it continues its life by fusing the hydrogen in its core. So let me tell you a little bit about where this map came from. So there are different surveys of hydrogen across our galaxy. We map the hydrogen galaxies across the universe now, depending on what we tune, what velocities we tune to look at. So this particular survey was with the Arecibo radio telescope. So it's the largest, it was the largest single dish radio telescope in the world. The new one is FAST in China. That is now the largest single dish radio telescope. I don't think it's actually gotten scientific data yet, but it is in operation now. They're starting to take some test observations. So because it's so large, we could see quite a bit of detail in our galaxy. You can see some of it in this image. You'll see even more when I show you the movie. And in other surveys, you're just getting kind of more blobs. Here you can see you're picking up filamentary webs of structure. These filaments we found through recent research that are aligned with our galaxy's magnetic field. So this is showing something about how gas is flowing along the galaxy's magnetic field lines. And when I show you the movie, you'll see kinematics of the gas as well. Just a little bit about Arecibo. This is what it looks like if you haven't been to it. It's actually suspended within the natural structures in Arecibo. They have natural sinkholes across this part of Arecibo, and so they did have to do quite a bit of blasting to put this in, but it is an amazing structure. You can zoom in on it just going down to Puerto Rico. It is still in operation. It actually did pretty well during the recent storm, which I hear you're going to hear more about, or you already heard about?
I'm done with that. I've heard
you already heard a lot about
yeah.
that. And so this is zooming in with Google Maps, right, just to depict with Google Maps what you can see there. It's also a relatively famous telescope. This crowd, sorry, but looking at the age distribution, I think many of you are familiar with these movies. I actually, when I give public talks to students now, I take this out because no one knows these movies. But and I don't think it's been featured in any movies since. So it was in both of these movies. GoldenEye, the James Bond movie. He blew it up supposedly, but he didn't really. And this is Jodie Foster in Contact, where she tried to detect ET with this telescope. What she actually ultimately detected the signal from was the Very Large Array, which I also use in New Mexico, which is an array of radio telescopes to get even more detail on what's going on with gas. Another slightly dated picture, but I thought you guys might be interested in this. This is actually myself as a graduate student and a collaborator in the control room at Arecibo. We used to go there to get all of our observations, but the survey I'll talk about now, we switched over pretty rapidly to an operator mode where they took all of our observations for us to cover the entire Arecibo sky. This is what it looks like if you want to get some exercise. You can run around the dish. So there aren't that many places you can go. The roads are pretty crazy there. The dogs will rapidly come after you. So often astronomers visiting there will run around the dish to get their exercise. It's 300 meters across, so you go around enough times. You're doing a 10K, it's a good workout overall. And this is the map that I want to show you that we achieved. So we surveyed the entire Arecibo sky that was accessible, and made, let me just get the cursor there, and basically recently released this to all astronomers. You can't really pick out the colors, unfortunately, but I'll go through this a couple times. So this is going through in right ascension. This is declination going there. So we cover from about 0 to 30 degrees in declination, and then all right ascension. So that's our sky, 13,000 square degrees of sky. And what you're looking at, the colors represent different velocities that you're seeing. Right now you're looking basically overhead. If our galaxy's here, you're looking basically overhead. The gas surrounds us everywhere, right? When you look around us, there's gas between the stars, and it has a thickness of, say, 200 parsecs, roughly. So you have a gaseous disk around our Milky Way. This is going through the outer galaxy here. So the outer part of our galaxy actually has a warp in the gas. So you actually see it get thicker as you look towards the outer galaxy, whereas we actually went through the inner galaxy earlier, and it's thinner when you look towards the inner galaxy because it doesn't have that same warp structure. Some things I want to highlight here, you can nicely see what I told you about those linear structures that are actually aligned with the galactic magnetic field. This is some research a graduate student and I are currently working on to try to figure out what are the properties of these filaments and why are they aligned with the galactic magnetic field. And then, so this is the inner galaxy here, the thinner inner galaxy component. And then the other thing that we can do with this data is look at the kinematics. And this is something we're also looking at those filaments in that context, looking at the flow along the filaments, looking at their velocity width, because that gives us an idea of the kinetic temperature of these filaments. And with the velocity information, we can learn a lot more about it. We can also study nearby galaxies. So how do we actually get the velocities? Do you guys know how we measure velocities in astronomy? I think most of you do.
Doppler shift.
Doppler shift, exactly. So what we're doing is we're looking for the shift in the 21 centimeter light that we observe. We're looking for either a red shift or a blue shift, and then that corresponds to whether that gas is moving towards or away from us. So as we look, in most galaxies are moving away from us out in the universe, except for the most local ones. In the case of our galaxy, we have quite a mixture, depending on where you are in terms of where you're looking and how the galaxy is rotating in that direction. But then when you look overhead, what do you see? You see a net inflow. So this is partially representing that there's gas above us that has a net inflow down onto us and represents some of the fuel that's starting to come in.
How thick, if you're looking at the galaxy edge on, how thick is that gas?
Yeah, for our galaxy, it's about 200 parsecs in the inner regions, but it can flare towards a kiloparsec in the very outer regions.
Wow.
But in the solar neighborhood, about 200 parsecs. But it's not, the thick stellar disk is about a kiloparsec, right? So it's actually not much compared to the thick stellar disk of our galaxy, but our galaxy has a comparable thin disk, which is where the young stars are forming, and the cold gas, which is the star formation fuel, correlates with the thin disk where the young stars are forming.
What percent of that is hydrogen?
This is all hydrogen. This is just detecting cold hydrogen. Yep, this is just hydrogen. What you do in terms of getting a total gas mass is you do a correction for helium. The molecular gas fraction is not that high for our galaxy, so it doesn't contribute as much, and then you can get an idea for the total mass suffering. And it's low compared to the stellar as well. It's about a factor of 8 down. Okay, you guys know all about Doppler shift. Okay, so what does a galaxy do with all this hydrogen gas? So I mentioned that a little bit before, but the gist of it is that this is what it needs to form new stars. So our sun, for instance, wouldn't exist unless our galaxy was continually bringing in fresh fuel to form stars. Our sun is a second generation star, right? About 5 gigayears old, 5 billion years old. And if you look at typical things that are thought to be Milky Way-like at, say, 8 gigayears ago, they don't have enough fuel to form stars up until, the sun's age or further, right? So the evidence out there all points that a galaxy needs to continually bring in this hydrogen gas in order to form stars. And so our sun's an example that wouldn't exist without our galaxy bringing in that fresh fuel. And then this is just the fusion process of the hydrogen going to helium and energy in the inner parts as the main source of fuel to create the energy for our sun. So the other thing I mentioned is that the gas is atomic. The hydrogen gas we're detecting is in the atomic form. So in order to form stars, you have to get the gas to be very cold and dense in molecular clouds where it can then collapse down and form stars. So this is just one beautiful picture showing the evidence of the molecular gas, the dust being the dark spots, with the ionized gas around it representing the birth of hot young stars. And they're basically ionizing the gas around it, so you get that nice glowing evidence around it. Has anyone taken pictures of this? Yeah, you have?
Yes.
Okay, great. How does it look here?
Well, through the scope I was using, small.
Okay.
You can see that.
You
It's
can
not-
see the pillars?
Oh, sure.
Yeah, yeah. Oh, great. Okay. Okay, so let's talk about where the hydrogen gas to form stars actually comes from. This is just not our Milky Way, showing you an example of another galaxy of M31. This is the stellar light distribution. This is the gas distribution. And these are some of the clouds that you see when you look up above that indicate this is evidence of the gas raining down onto the disk and fueling, in this case, M31. So where does this gas actually come from? Generally, what is the prediction is that there are two modes a galaxy obtains the fuel to form new stars. The first mode is referred to as galactic cannibalism because it's basically the consumption of smaller galaxies. The little dwarf galaxy, the Leo 1, is one example, a prime example of what will be future fuel for our galaxy. In the case of Leo 1, though, it's already stripped of its gas. So once we gobble up that galaxy, it'll be mainly just stars and dark matter that we'll get at that stage. But that galaxy had gas at some stage, and so at some point, our galaxy also took the gas from that little galaxy. The other way we can get this hydrogen gas is rain of gas along cosmic filaments. So when I say cosmic filaments, structure in the universe is such that you have these filamentary distributions of mass, and so the galaxies tend to lie along these filaments, and the gas between galaxies flows into these dense concentrations where the galaxies are. So this gas flow can actually feed a galaxy as well. This is a more difficult thing to observationally say is definitely happening, but I'll say a little bit about this. Both these are predicted from simulations of galaxy formation as well. So let's start with the first one, consume other galaxies, galactic cannibalism, and focusing on our Milky Way. In the case of our Milky Way, it very clearly is undergoing eating other galaxies. So this is a cartoon of what this data shows. This is supposed to be the Milky Way, and this is the large and small Magellanic Cloud in the southern hemisphere observable. And you're seeing the stream of gas being pulled from the large and small Magellanic Cloud. And this gas will then rain down onto our Milky Way galaxy and fuel future star formation in our galaxy. Has anyone seen the large and small Magellanic Cloud? How many? A couple. Yeah, if you can, it's stunning. You go to a dark site and they're beautiful on the night sky. I think most of you might know this, but they were named by Magellan because he actually saw them when he was exploring as little smudges that look like clouds on the night sky. So they're the one galaxies that have this weird name of cloud, even though they're both galaxies. So this is the actual data. So this is the same gas. This is the atomic hydrogen gas. This is the large Magellanic Cloud. This is the small Magellanic Cloud. And you can see that these streams of gas are quite complex in structure. In this region, the clouds are moving in this direction. In this region, it's more diffuse, not as much there. And then the trailing stream, there's a lot of gas there that's being stripped from the system. This is a rough picture of what it looks like in the optical, so to give you a comparison point. So in the optical, it's not clear that these galaxies are undergoing any type of interaction. So this is, again, the point that you need these multi-wavelength images to really figure out what's going on. So they look irregular in structure, so that hints that something is going on. But it's really only when you look at their gas distribution you see what's really going on. They're interacting with both each other and also with our Milky Way galaxy. So how is the Milky Way actually, what's the process that the Milky Way is using to consume these galaxies? Do you guys know this? Any ideas?
Gravity, more than
Gravity, yeah, that's one. That's definitely one of the major ones. So there's two main ways that a galaxy consumes other galaxies and creates the type of structures you just saw. The first is tidal forces, or just gravity, and the other is something called ram pressure stripping, which I'll say something briefly about. When you're talking about tidal forces, you get these tidal tails. I pointed out that there was a structure in the foreground of the system. The system's moving this way. There's a stream here and there. This is a simulation. This is stars. But what's happened here is you had a dwarf galaxy going around the Milky Way, and what happens is you get these symmetric streams of stars pulled from the galaxy, and you get these beautiful streams of stars encircling our galaxy. And we observe these as well. So what I showed you is an example of a gaseous stream, but these streams of stars that encircle our galaxy are being observed quite readily, and there's many now that have been discovered. This particular one that Professor Johnston was simulating is the Sagittarius dwarf galaxy, which has multiple wraps going around it. In terms of thinking about tidal forces, where's the other place you've heard of tides predominantly?
The ocean.
Yeah, the ocean, right? So what you're talking about with tides, it's similar, it's somewhat different, but it's a similar analogy, right? In terms of what causes tidal forces is a difference in gravitational pull. So the gravitational force drops off as 1 over the distance squared, or in this case we have it labeled as r, so 1 over r squared. And so this difference in gravitational pull on the near and far side of the Earth results in a compression or stretching, and because the water is more compressible, you end up with tides on the near and far side. So going back to the movie then, you can think about, I can get going again. Almost. There. You can see as this is going around, you're getting kind of something similar going on here. You have a difference in gravitational pull on this side and this side, and the net result is you pull the middle part away from the far side and the near side is pulled towards it, and you end up with these symmetric streams as the galaxy goes around the larger galaxy. Okay, so thinking about this system and tidal forces, so there's definitely some evidence for gravity and tidal forces from the Milky Way ripping apart this dwarf system. Because you see, as I mentioned, the system's going this direction, you see this stream and you see this stream, so there's a symmetric structure there that you expect. The tricky part here is this is gas, and there's something weird going on with the gas distribution here. One, this stream is very offset from the motion. The motion is more like along that plane, so it's more like in this direction. So it's skewed in terms of the motion. This is much less massive than the trailing stream as well. So there's additional forces going on when we talk about the gas. Its hydrodynamic forces need to be considered. And the main hydrodynamical mechanism that we talk about when we think about stripping gas from galaxies and feeding the Milky Way or feeding other galaxies is something called ram pressure stripping. And this is a movie that depicts ram pressure stripping. The idea here is you have a small dwarf galaxy and it's moving through a low density material, or you could think about it as a wind. An analogy might be if you're blow drying your hair, right? There's a wind from the blow dryer, or you stick your head out the window and that pushes your hair back, right? So you can kind of think of it as something like that. The gas in this dwarf galaxy has basically a wind acting on it as it moves through a very diffuse low density medium, and that is stripping the gas from that dwarf galaxy. It does not act on the dark matter in the stars, right? So this is a mechanism that only is acting on the gas particles, gas interacting with gas. And so this is an efficient mechanism for a galaxy to consume gas from another galaxy that is distinct from what happens with the dark matter and the stars. And so adding this mechanism in as important as well can help explain the overall structure. It's a combination of tidal and ram pressure forces that is stripping the material that will feed the galaxy ultimately. Are there questions on this?
How far would the gravitational field be around the galaxy that would cause gas to trap into it? I mean, in other words, if there's gas out there in the universe, it can just go past us and not be sucked in. How far is that field? How far is it make?
So you're wondering like about the gas distribution maybe?
Yeah, like how far does it have to be away before it can't be pulled into the galaxy?
Okay, so it depends on the orbit of the galaxy and the masses of the two galaxies in terms of when it would be pulled in. So when you think about a galaxy, you have this small little stellar and gas component, or at least a denser gas component, a denser stellar component, and then you have this massive dark matter halo that goes out to, say this is 25 kiloparsecs, it goes out to about 10 times that in that direction for the dark matter halo. What's in that dark matter halo then is this low density gas that is bound to this galaxy. So what happens is a little dwarf galaxy comes in and it has an orbit such that it does come into our galaxy's gravitational influence, and when it has that effect, it also is moving through a medium that's within our galaxy's dark matter halo. And so when it passes through that medium within our galaxy's dark matter halo, then the two gases interact with each other and it strips the gas from it.
So do we know what's the furthest that we've observed? What's the furthest smaller galaxy that is now trapped into our gravitational field?
Yeah, so
We're talking
usually,
about
yes.
10 light years, we're talking about 100 light years, I mean.
So usually we take the virial rate, what's called the virial radius as a limit in terms of if you don't know other things about it. If it's kinematics as such, it can come in and then go right back out, right?
Yeah.
But otherwise, we typically will take the virial radius, which is about 250 kiloparsecs. You think in parsecs as well. So divide by 3.26, right?
Okay.
Or no, wait, multiply by 3.26. And that gives you an idea in terms of light years. Yeah.
Is the larger galaxy being stretched by the smaller one
Is the larger galaxy
as well? So the
Oh, yeah. So that's a very interesting question. So that's an active area of research. But one idea is that, remember I mentioned our galaxy has this warp in its gas in its outer regions? That could very well be due to the Magellanic clouds. Basically, they pull on, it's a mutual force, right? So even though they're much less massive than the Milky Way, they can still affect things depending on how close they get. So there's been a couple papers out that talk about the Magellanic clouds creating the warp in our Milky Way's gas distribution.
So,
Yeah.
you used your hand.
Okay. There are elliptical dwarf galaxies that basically just collections of stars that have been very, very hard. And it's
Yeah.
not really clear how they're formed. Is this one of the mechanisms that they basically, the gas was stripped and they just orbited and finally just settled into a ball? Or is there just another mechanism for possibly making these collections
Yeah, so
of
for
ancient
ellipticals,
stars?
there's two formation channels. The primary one, though, that you're referring to is it has to be a merger of two larger galaxies. Like the merger of Andromeda and the Milky Way will eventually form an elliptical galaxy. The reason is a merger like this doesn't change the spiral structure of the Milky Way. It's not large enough to mix it up that much. It's also going to be a process where much of the gas more rains down onto the galaxy rather than a collision of two massive things where the gas collides with each other and you get this irregular mess with lots of star formation that settles into a bunch of random orbits where it's used up all its star formation fuel, which is an elliptical galaxy. So not in this case, but if they were more massive than or comparable mass, then yes. Yeah.
So do we have a sense of what rate of flow overall of gas needs to enter the Milky Way area in order to sustain it?
Yeah, that's a great question. So we think our star formation rate is about 1 to 3 solar masses per year, depending on who you ask and what data you use. And so we think the accretion rate has to be at least that. Most people think it has to be a little bit higher than that, right? That is not exactly 1 to 1, but at least that. So we're looking to bring in about 1 to 3 solar masses of fuel per year. And the evidence is looking at the metallicity distribution of the stars in our Milky Way is that it's needed to bring in that rate of fuel for the past, say, 10 gigayears. So it's a lot of fuel it has to bring in.
mechanism that would provide that rate? I mean, that's-
Right, so you're actually asking the perfect question. So this is one mechanism I talked about for how a galaxy can get fuel. What about the other mechanism? So I talked about consuming other galaxies. We actually see that, we know what's going on, and we understand it at least at some level. What about this other method, though, the rain of gas along cosmic filaments? The main reason we need that method, independent, well, I'll talk about there's evidence for it as well, is because when you look at the satellite distribution around galaxies, there just isn't enough there to give you that type of accretion rate. So no matter how you work the numbers in terms of figuring out what ones are missing, there's a whole missing satellite problem, etc. You can't get the numbers high enough for that to be the only source of fuel for a galaxy to keep forming stars. So both the observational evidence and also the fact that simulations predict this, and we know there's all this gas out there, indicates that you need some fuel coming in along the cosmic filaments as well. Just briefly, so this is just an older map of our local group. The number of dwarf galaxies in our local group has increased tremendously. We're up towards 50 now, and this is because of the new deep surveys that have been done, and we're able to pick out these little smudges on the sky that I think you guys would never be able to detect. The Leo one's been known about for a while, that one up here, so you could definitely go for that. One dwarf galaxy that I am very fond of is called Leo T, so again, through the constellation of Leo, but much further away, it's an extremely, extremely small galaxy that also has gas. And so it's fascinating. It's the perfect like seed of galaxy formation from the early universe, kind of a pristine little seed.
What's the diameter of a small galaxy?
The diameter of a
when we saw
small
small, what's
galaxy,
small?
like a couple kiloparsecs.
And would that have
Actually, the Leo T is only 300 parsecs, actually, yeah. So the regular dwarfs are like a couple kiloparsecs, but going down to the ultra faint, really small ones, then we're in few hundred parsecs.
And there are 50
going
of
down
them.
the scale.
There are 50 of these?
At least something like that. They're being discovered on a regular timescale. There's something called the Dark Energy Survey currently going on. There's in the south that is uncovering quite a few of these. So these are basically deep imaging surveys that are then able to capture these little smudges that weren't seen before. There's also pan stars in Hawaii that's been released. That's not quite as deep as Dark Energy Survey, but so we're definitely finding a lot more, but it's still not enough in terms of continually fueling the Milky Way as star formation fuel. Just to give you a context, I think I put the H1 over here. So this is the LMC SMC. So this is quite close to the Milky Way compared to many of the other dwarf galaxies, and it has these streams falling off it like that. I think I also, and this is the case of M31. What you see is this gas here is going out towards M33 over here. Okay, so let's talk a little bit about the second mode. I don't have quite as much on this, but I'm happy to answer quite a bit of questions on this because I work on it. The second mode, rain along cosmic filaments, this is a simulation image from Professor Bryan at Columbia showing you how these dense parts are where you have galaxy clusters, and then you have what has very little galaxies in it, but there's still gas and dark matter along this filamentary structure. And the general idea is that these baryons located in this filamentary structure flows down and fuels the galaxy clusters and the individual galaxies, the larger, denser dark matter halos. Yeah.
What's the scale on that picture?
I actually don't know. I should note that, but I mean, yeah, I mean, if I had to guess, this is a massive galaxy cluster, so this would be about 2 megaparsecs across right there. So it's a large chunk of the universe. Yeah. So the next simulation I'm going to show you is pretty complex, but it's showing you the evolution of a Milky Way galaxy. We did this with Professor Bryan and a postdoc at Columbia. We ran one of the highest resolution simulations of a Milky Way galaxy forming, and what we found is this type of thing in terms of what we expect for the hydrogen gas. So what you're doing is you're stepping through in time. Up in that upper right corner, you're seeing the redshifts marching down towards redshift of 0. And then this purple material is showing you largely the material coming in along the cosmic filaments. So this is the galaxy being fueled by this gas coming in along the cosmic filaments. And then these denser clumps coming in, those are satellites that are being accreted by the Milky Way-like galaxy as well. So this is the disk in this inner region. The red stuff represents the densest stuff there. Okay, we didn't bring it down to z=0 in this simulation. You can see basically at earlier times there was a lot more coming in. There was more star formation, so you needed more coming in, and then it settles down a little bit. in terms of the amount of material coming in at later times. But this is basically depicting the two mechanisms that we think must be active in order for a galaxy like the Milky Way to keep growing and forming stars throughout time. The accretion of the satellites together with this rain of material along the cosmic filaments. In terms of observing the second mode, there's several lines of evidence that we actually are observing the second mode. The one I'm going to flash up here, this is just going back to the simulation, and it's highlighting a couple of the denser pockets of gas, which actually have distinct origins. And this is a map showing observations of gas around our Milky Way galaxy. So this is if you looked all around our Milky Way galaxy, what do you see in terms of gas that has pretty high velocities, and most of it is moving towards us. Not all of it, but most of it is moving towards us. And you can see there's quite a bit there. The shaded represents the cold hydrogen gas, and these little circles represent gas that is hotter, that was detected from absorption line experiments. So all this material, much of it is of unknown origin. This is the Magellan extreme, so we know where that's coming from. But all of this stuff, we actually don't know where it came from. And so one possible origin is that it's gas that has come in along those cosmic filaments. And there's several tests we can do to see if that's the case. Okay, so I'll go ahead and end there and then just take questions from you. Just to wrap things up, this is a map, should depict an image, a drawing depicting some of the structures and how a Milky Way grows with the accretion of gas from satellites, the Magellan extreme, and then up above we have what are called HVCs, or high velocity clouds, raining down onto the disk. So we can map the Milky Way gas to trace the processes of accretion. We see it's growing both with cannibalism and most likely the gas flows along filaments as well. A lot of work to be done on that latter point, I would say, observationally. And then this growth of the Milky Way provides insight into how galaxies grow throughout the universe, because we can't detect that gas around most galaxies. It's too low of density. So using the Milky Way as a template for how this is going on has been key for understanding how galaxies grow. So I'll go ahead and take questions there. Thanks.
What if you start from just gas? How do you start the first galaxy? How does the first galaxy?
The first galaxy.
We got all these metals in our solar system. All this gas is hydrogen, so that's not going to give us any.
Yeah. So when we look back at the earliest times we can detect, we always see some metals. Those metals, the origin would probably the first stars had very short lives and injected metals into the gas distribution, and then from there the first galaxies are thought to have very powerful jets and such that spew any metals created in the galaxy out. So the first one, the way it gets going, right, is you have the dark matter concentration, the gas, the baryons follow the dark matter and accrete onto that dark matter halo, and then star formation proceeds, etc.
So would a dark matter created a black hole?
No, that doesn't work that way. But it could, in the sense of creating a very massive star that creates a seed of a black hole in terms of the gas going into the center and creating a very massive star. Yeah.
That's my question. Do black holes have any effect in attracting, like gravitational tidal waves, this gaseous structure? In other words, does the gas head towards the black hole?
Yeah, so this is something I'm always telling my class. Black holes do not suck. Black holes, their gravitational influence is actually, so if a star is massive enough to become a black hole, the only place that the gravitational pull is extreme is in the previous radius of the star. So here's the radius of the star, it becomes a black hole, basically a point of infinite density. The strong gravitational realm is basically what the previous radius of the star is. It isn't going to reach out and pull stuff here. So the only way a black hole can accrete matter in the thinking about the gas is if the gas is somehow already moving in that direction. And then when it's moving in that direction, then it is sucked in once it gets close enough. But it has to get very close in order to have that occur. Yeah.
When you talk about the gas falling in, what's the unit of density you use for how much gas we're talking about?
Yeah,
Particles
so usually,
per cubic
yeah,
light year?
exactly. We actually do, so when we're doing observations, we measure atoms per square centimeter. And then if we have a distance to the gas, where it is and stuff, we can convert that to atoms per cubic centimeter.
So it
That's how we
is,
measure
so
it.
it's in units of atoms, tens, ones per cubic centimeter.
Yeah.
And what kind of density?
That's the density.
Yeah, so what kind of densities?
Well-
So out in the halo, the densities are very low, like 0.1 atoms per cubic centimeter. When you're in the disk of the galaxy, it's much higher, like more hundreds. It can be even higher if you're in molecular. But I mean, compared to the density of air, it's absolutely
Like say
nothing.
in
but,
one of the
yeah.
streams, like the Magellanic stream, can you measure the
Yeah.
density within that? Like what is that beyond our disk? What is that
Yeah,
density
yeah. So
coming
the
in?
density
Filament.
of this stuff compared to our disk stuff is pretty low. It's down about a factor of 10 from what's in the disk. Yeah. Yeah.
Does the distribution of dark matter reflect the filamentary structure of the real matter?
Yes, yeah, so they follow each other. So the way it's set up in the early universe is the dark matter dominates, and basically the dark matter then is shaping what happens with the rest of the matter in the universe. So they follow each other, with largely the dark matter leading.
So if the magnetic fields determine the flow in the filaments, they
So, yeah, so I probably confused you because I brought in that research. When I was talking about the filaments here, I'm talking about different filaments than what I showed in the movie. So the magnetic field could definitely be related to these cosmic filaments, but when I was talking about the filaments in the movie, so this is large-scale gas flows in the universe. The filaments in the movie are very, very, I can shut it down, are very small structures within our galaxy. So they're somewhat distinct, but they're all representing some form of gas flow, so there could be a bulk relationship with the larger filaments too. We just don't know that yet. Whereas in our galaxy, we actually have detailed information on the magnetic field, so we can make that link between those small filaments and the galactic magnetic field. I'm glad you asked that. Yeah.
So the cosmic filaments are gravity or magnetic wave?
Oh, the cosmic filaments is largely gravity, but to be honest, astronomers are very far behind in terms of understanding the structure of magnetic fields in the universe. That's something we have a long way to go on. But generally, the way the simulation's set up, they usually don't include magnetic fields at all. So this is all dictated by the structure of matter in the universe. The structure of matter in the universe is set up by the initial quantum fluctuations after the Big Bang that are left. Yeah.
Excuse me, for the galactic filaments, I might have missed this, but you're following the 21 centimeter for hydrogen. Are you implying, or did I miss something, that maybe the heavier elements are going along the same filaments?
So the heavier elements are largely when you start talking about molecular gas,
Mm-hmm.
and that's where you're capturing largely that. So yes, in general, all the gas phase is following that magnetic field structure, and the overall, what we have for the theory is that what's going on is the atomic gas is flowing along the magnetic field filaments, and then when they converge onto the denser molecular filaments, and so they actually expect them to be perpendicular to the denser molecular filaments. And there's some evidence for that, but this is again something people are working on, yeah.
Okay.
Yeah.
Thank you.
Uh-huh.
Taking it back to the theme I was harping on before, I'm afraid. But does the ledger balance in the sense of, is there enough gas over the history of the universe up to this time coming in along filaments, understanding that there are also collisions going on that help that flow,
Yeah.
to explain where we are now in terms of the amount of mass that's present in the Milky Way?
Yeah, so the way that you reproduce galaxies in what are called cosmological simulations, which are simulations that start from the beginning of time and go on, is by having that combination of the gas flow along cosmic filaments and the accretion of the satellites. And what they end up with then is reproducing this large-scale distribution quite nicely. And then for the galaxies, they're usually overproducing the number of stars a little bit. But they think that's mainly due to the feedback effects. That's the problem there. So the thinking is from the simulations that you need this amount of star formation fuel accreting onto the disk. That's consistent with what we see out there in the larger universe. And then when we look at the observations, the observations indicate we need that too, but we aren't really seeing that accretion yet. We know the matter's out there, but we're not seeing it flowing on like that. So that's one of the problems with that accretion along cosmic filaments. It looks so beautiful in the simulation, the gas is nicely flowing in, we just don't see that kind of beauty in the observations yet.
Do you think we have the capability to see it?
We're
more
getting
outside?
better, we're getting
Oh, I
better.
understand.
Yeah,
I'm just wondering if
HST has
it's a-
kind of opened that up, and now we're mapping these low density gas. We've started to create these beautiful maps of its distribution. We're starting to learn more about how it's moving, and so it would be headed in the right direction. Yeah. Okay, I think I can take one or two more questions. Yeah.
Between the two processes you described, were the tidal forces and the ram forces. Tidal forces are gravitationally based, so very long range forces. The ram, does that require collisions for transfer of momentum? And there's very short range.
Yeah, it's
and
gas
at such
particles.
low density, aren't the probability of those collisions very low?
No, so there's basically, the effect of the ram pressure stripping is dependent on the density of the medium it's moving through, the density in the galaxy itself, and the velocity. The velocity is key as well. So you do need to consider all those factors, but in cases like a galaxy halo or a cluster of galaxies, there's plenty of intragalactic gas that can do that stripping as long as you have something moving quickly enough.
It's funny, my question was on the same thing. Your simulation showed that it was fast and turbulent. Is there any evidence that it can be slow and laminar?
I don't think so. I've never seen that. Yeah, it doesn't make sense in terms of the galaxy velocities we observe. Yeah,
Mhm.
yeah, it's interesting. Yeah. Okay, well, thank you so much.